the main goal was actually like many people are like currently working on the large language model. So in this talk, like I want to see actually like can we, use actually speech interface for the large language model, and then what are the things we can do it. This is like a still a some of the things are still exploration, and some are actually already we put it in also cloud solutions. Some are already there. So basically the motivation was actually like we already developed like some solution like earlier, like even the speech community, like many people who are working here also, and also in the talk also many people worked on this. So we developed the ASR system, we developed the TTS, and then can we also give actually like audio interface, and some of it actually already doing it. For example, in chat GPT, if you know, I think every day you can see that like they come up with some new solution. They also integrated audio also, audio interface to the LLMs, and Google also in Gemini they tried it. So here actually like what we tried is like can we also do that task actually first of all, and then second is can we do for Indian languages, because it may not direct straightforwardly work actually for Indian languages, because there are two things. One is actually like the current LLMs, what are the Indian LLMs? In ChatGPT, what are the LLMs we have? It cannot understand the Indian context. Second thing is we don't have any data set to train actually to completely speech to speech. For example, if you are thinking speech LLM, input will be speech and output also will be speech. So we don't have such data set also, which is for Indian language at least. So we need to rely mostly on the synthetic data. There are some data sets are there, but there is no fully, end-to-end data set is not there, or if it is there also a very limited data set. So that's why we started exploring that. So I thought like this exploration we can discuss in this talk. So with that motivation, I will start my talk today. Yeah, sir, can you go to next slide?
Yes, I am in next slide only.
Sure. Okay. Yeah, so basically, like I want to initially give a brief introduction about the speech LLMs, and then what are the applications we can do with the speech LLMs, and then after that, like we will see actually how this evolution happened. Actually, is it like just now started the LLMs, or like it was there and beforehand, and then slowly this transition? So that part we'll go through it in evolution, and then what are the different components are there in speech LLM? So that like can we with the just with current LLM can we directly interface what modules are required actually to develop this speech LLM, that we will discuss, and then how to do this fusion of speech and text, right? What are the modalities we need to do it actually to combine speech with the text, and then we can feed it to LLM. So that technologies we can see, and then the training strategies, like how people tried it and how we are doing it. In the end actually like what we tried in Krutrim, so that we'll discuss, and then finally some future direction, because not all the problems are solved, some problems solved and some are like exploration. So with that actually I will introduce today's talk. So in the as I said earlier, like in the language model, like it explored for multiple tasks in NLP, and many like you see that in ChatGPT, you can see that it can do multiple tasks like summarization. It can do actually, it can do. You can also write the code and everything. Multiple tasks it can do. So here actually like then people also started like exploring multiple modality. For example, vision, I mentioned it here actually, clip or DALI, where it will, if you just give some text, it will generate image using some kind of diffusion model with the LLM, with a combination of LLM. Or like in speech also people explored, the early exploration is from the Google audio palm, which they tried, and then slowly it moved to speech GPT, Salman, or like Moshi, where actually we can do a dual channel. For example, you can speak also actually parallelly, it can listen also. Dual channel they tried. That's a very recent work actually in Moshi. And then like in video integration also, can we also have a video interface? So that also a video LLM it's there actually. So multiple modality people are started using it. At least for the English language, multiple methods are there, but for Indian language very few methods are there, still people are exploring. So that exploration we started, that we'll discuss in today's talk. And if any question in between, kindly let me know, so that I can answer it actually during that time only. Okay, so in speech LLM, basically, as I said, we are integrating speech modality for the LLM so that like we can understand actually what are the modality. I mean, what are the things are there in speech? For example, who spoke and when that person is spoke, or like is what is the kind of emotion is there. So that kind of understanding we can do it, as well as generate actually. Like, can we convert from speech to text, speech to different languages? Can we convert translation task? Or can we also do some kind of spoken query? For example, you ask some questions. Currently, we are doing in ChatGPT like by typing it, and we can also do it in speech modality. We can also do it. I mean. Like what are the questions we can ask and it will answer it, so that kind of interface. So these are the things people try it out, and also like generation, finally the output also should be in speech. That's why in the one of the task I mentioned it, speech to speech, and emotion recognition and speech representation I already mentioned it. So these are some of the application. And evaluation of speech LLM is initially like if you remember like pre LLM stage, the first one, the left part, whatever I mentioned it here, where actually like it's a, you can think a traditional acoustic model, where actually traditional ASR models we are doing it, audio will be input and then acoustic model, and then still we are using language model. I mean, this is a pre LLM stage where I mean, LLM means it's a large language model. Basically, it's trained with a large amount of data and then large number of layers. So that like whatever the data available in the, I mean, right, I mean, in world, right, we use it, and that's why it's got a very large language model. Whereas still people are using in our earlier ASR, we are using that acoustic model, language model was there. So you can think like this is a pre-LLM. Still, we are using that language model, but in a small amount. I mean, either n-gram or like maybe a simple RNLM model, something like we are still using it. So that you can think like the initial study, actually people are doing that. And then slowly actually people moved from acoustic model and then language model also. We try to see actually can we use same architecture. For example, we use the transformer initially with the LLM, but then we also moved that transformer even in acoustic model. Even in the language model, we tried it. So by doing that, actually, the acoustic model, we got the better improvement. For example, in the speech transformer or conformer model, like we got better accuracy in terms of currently like conform is one of the state of the art speech recognition module. So, but it usually basically it uses transformer architecture internally, and by using that actually we got a better number actually. So I mean, what are the architecture used in LLM, people still used in ASR also, we got the better results. Similarly, like people started using can we also use a lot of unlabeled data, like how people using BERT kind of model or like LLM kind of architecture. Similarly, we tried with Hubert kind of architecture, where we have a lot of unlabeled data. And with this unlabeled data, can we try to predict the, I mean, can we utilize that properly? So what we done is like, can we predict the, I mean, for example, in Hubert kind of model, we mask the, I mean, input audio and then try to predict that masked portion. With that, actually, we get a very rich representation of speech features. And when we, on the top of that, if we just add one layer of ASR CTC layer, then we got very good results in Hubert. Similarly, Whisper, this also uses, I mean, slowly that moved actually from like initial speech transformer to slowly it moved to till Whisper level, and we got very good results. And also another important thing is Whisper, when they are doing it, they are not only did for single task, they tried for multiple like task like single model. Whisper model is able to identify the language identification, or it also gives the timestamp of the like where which person spoke, as well as it's able to do the AST also. I mean, speech translation. For example, if you give the input will be in French, it can convert to English. So this kind of multitask people tried in this early LLMs, or like a Whisper kind of architecture. Sir, any question on this? Oh, okay, I will continue then. So now actually in the current speech LLM, so that is the bottommost part where people started integrating the LLM with the, I mean, with the speech. So large language model. So instead of the smaller language model, like where actually the number of layers are like 10, 15 layers. So now we expanded and more number of layers we used, and then more amount of data we used it, and then integrating the audio with that. Actually, that's the main thing. And here also again people started using different type of features. Like one is discrete features, and then continuous features. Discrete means the what are the output we are getting from audio, that actually they discretize and use some like a fewer number of units, and then try to model using the LLM. Whereas in the continuous representation, as it is, we can use the same features and continue to use it and LLM. So both have some advantage and disadvantage. And you can see that like in that current flow, right? I mean, people started using for multiple application. For example, in discrete sequence modeling, people started using Valley for speech synthesis application, or like audio palm or any GPT, or Valley 2 also came for speech synthesis. Similarly, in continuous modeling also, the Salman, which we can do it actually like multiple tasks, like translation we can do, or like we can do spoken query recognition. I mean, we can ask question, it will answer it. So multiple, even for AS also people tried. So there are both advantages in continuous as well as discrete. So people explored this in current speech LLM. So this is the how and the LLMs are evolved actually for this speech use case. Sir, okay. Coming to what are the components are there in speech LLM. So for example, like when we need to integrate our speech or the audio interface to the LLM, there are multiple modules that is I listed here. One is speech encoder, where like when we speak, right, that will be in audio waveform level. So how to convert this waveform, and that we can, and we need to convert some intermediate features, so that feature we can put it to some kind of I mean, we can put to LLM. So that actually we can do it using the speech encoder. So it's basically like it extracts some kind of features. And like people use multiple speech encoder, like for example whisper is one of the method. And then we can also use Hubert, and then Canary is from NVIDIA, we can use it, or Wave2X. These are some of the examples. There are some advantage and disadvantage of all these methods, but like Whisper is actually for the speech, some of the tasks Whispers perform better compared to all the methods. And then after the speech encoder, we will have the adapter. Why we need adapter means basically speech will be in some sampling rate, whereas text actually will be in some different sampling rate. So we need to convert, even though after passing to the audio to the speech encoder, we'll get some kind of features or a speech representation. And from that dimension, we need to go to the LN space. So we need some kind of projection, or like convert from audio feature level to text feature level. So for that purpose, actually, we are using this adapter. And we can use simple linear layer kind of projection layer, or like there is a Q-former. Q-former is again one kind of transformer only, but it is basically, you can think like basically we're asking some kind of questions. So that's why they call it as a Q-former. Question against the speech features. So some of the weights of the speech Q-former will act as a query in the transformer, and then the speech input or the speech encoder output, we are giving it as a value and key, so that it will give some kind of features. That feature we will put it to LLM. So that people do it in Q format. There is one more method called CLAP also. It's a contrastive learning audio pre-training model. So these are the different adapters people use it. And another important module is like, as you know, like since we are integrating with LLM, LLM is anyway required. So we can use multiple LLMs. So chat GPTs are the one of the famous one. But then some of the open source are like Llama, Quen, or DeepSeek. I think DeepSeek is one of the currently it's a trending one. Like if you go to the LinkedIn, you can see only post about DeepSeek only. So these are some of the common methods. I mean, basically, like you can take some combination of this and then integrate with any one of the LLMs. And if you have the perfect data set, then it should work actually to integrate our features with the LLM. And then finally, if you want just the text output, then the first three module is sufficient, because basically like speech input, and then if you need just text, then the first three module is sufficient. But if you want to also generate the audio, then we need some kind of mapping from the text token to speech synthesizer, that we call it as vocoder. I mean, this is a vague term. We can also use some multiple module in between, but then vocoder is a very important module, like to convert from the speech token, I mean, our text token to speech tokens, finally, so that it will be in audio waveform level. So that is done by vocoder. So some of the famous method is hi-fi, GAN, or like quasi voice. So these are the some common methods, and these are the some important modules required for the speech LLM. So next slide. Okay. Now we understood that, like till now, that what are the different components required. Now actually, like we will see actually what kind of different architectures are there. Like here actually in this example, I am just showing S2T. S2T means actually input will be audio and output will be text. So for example, if you see here, there is a audio encoder is there, which will convert from audio to some kind of embedding space. So you can think like some kind of feature extractor. Audio features is there, and then there is a conversion module. Basically, it will convert. It act like an adapter that I discussed earlier. So it will convert from the audio space to text space. So that is done by the conversion module. And once we have the text, I mean, the input from the conversion module will be some kind of features which is closer to the text embedding space, and then we can pass it to the LLM. So this text embedding space is act like a LLM. And then finally, I mean, text decoder, which is this text embedding space is still an intermediate space, and text decoder is basically a LLM. So which will give the next. It will try to predict the next tokens. And for example, if you're using it for the speech recognition task, audio will be the input, and then it is try to predict the next token. That is like what is the transcription, right? I mean, word by word, or the if you are using a BP as a token, then BP tokens try to predict next tokens try to predict. So this is a like a very early version of you can think like a speech to text, where only audio only input will be only one interface audio, and output also only in one modality, that is text actually. So one input modality and output is also in one modality. Next slide. Yeah, so next slightly advanced version is actually like we can also give two modality. One is input modality will be audio, and then also there is a one additional prompt we'll give actually. So prompt is actually basically, for example, if you want to, for example, there is a audio is there, and then in the this prompt, right? I mean, in the text, the left side actually, what is there in the text prompt, task prompt, will say that what is there in this audio, or like can you transcribe the audio, or like can you mention, can you translate the audio? So some kind of this prompt, right? That is we can we can give it to the LLM using this text task prompt. So here actually both audio input as well as text input will go actually. So two kind of input we are giving it, and output will be always in text actually. So basically we are input will be two modality, audio and text, and then output will be in the text. That's why they call it as speech text to text. So that is the nomenclature they are using it. And the remaining all, it will be remain same. Only thing is here the audio features and the text features we are combining together and fusing together before feeding to LLM. So what kind of fusing we can do, that I will tell in next few slides. But currently you can think like we are fusing audio as well as audio features as well as text features before feeding to LLM. A text decoder you can think like it's a LLM, and it's trying to predict the next token prediction. Is try to do that. This is one of the most commonly used architecture. Next is actually like here input also two modality and output also will be two modality. So for example, as I said earlier, like input, I already explained it. One is audio input as well as text input. Text input will be like you can ask some kind of questions. Like first you say the audio, and then can you also I mean, we can also type and say that translate it, or like ask some questions, analyze this audio or summarize this audio. That kind of questions we can ask with the prompt. So imagine actually like while training, what we do is we'll have the audio pair, and as well as the text pairs also will be there. That is will be for output, audio text, and then some kind of output. But then we can also have the additional prompt which says that what to do in this for this pair. So you can say that like identify the language and then translate it, or like you can say that summarize this audio, something like that we can say. So that is the job of this task prompt. And in the output level, we along with the text prediction, we can also convert this text into some kind of speech units. So that is using this vocoder. So here actually in the output mode also we have the two modality. One is text modality, and then second is audio modality. So that's why it is like both in input two modality and output also two modality. So that's why it is called S2 ST to ST. And and these are the like commonly three different architecture people use it in the speech LLM. And you can think like, for example, if we are going for multimodality, then you can, along with audio and text, right, there's a one mode vision modality will be there, or like video modality will come. So like that is multimodality LLM people try it out. But for this talk we are just talking about audio as well as only audio and text only we are talking about. And next thing is fusing, how we need to combine the features, right? So for example, even though actually we are using audio, and then also I said that there is a task, what kind of task we need to do. Like for example, if we need to mention that can you do translate this audio, or can we say that analyze this audio and then give some response, something like that. To say that we need additional input that is in the left side, right? The text input is there. So when we pass this text input to text encoder, we'll get some features. And similarly, for audio also, if you pass it to the speech encoder, we'll get some features. After like projecting, we'll get some kind of features. But then how to combine this? So there are multiple methods. One is like a direct projection. So in the direct projection method, what we do is we use some kind of projector. For example, in this diagram, you can see that between that green box and then orange box, there is a one projector is there. So that projector will convert from audio embedding to some kind of aligned audio embedding. I mean, we are converting to some kind of text space, or like some different dimension we are converting, where so that like the dimension of that it's equivalent to the text embedding space. Then after getting this, both text embedding as well as the audio embedding, either we can concurrent it together, or we can keep it, fuse together, and then before passing to LLM, we can do this. So basically what's happening is we are converting audio into text embedding space here actually in this modality that people call it as a direct projection. And remaining will be similar. Remaining part of the LLM and speech LLM will be remain same. Only here we are talking about how we can fuse audio and text before feeding to LLM. So direct projection is one of the method. Next slide. Okay. So in the second method is actually like we use some kind, we call it as a token mapping, where first we combine the audio as well as text token. For example, if you see in this diagram, the green color will be audio tokens, and then orange color will be text token. We combine together, and then we apply the additional text encoder. So instead of projecting beforehand, we are projecting in the later actually. So before feeding it to LLM, we are having additional text encoder, which will convert this concurrent tokens into LLM space. So this will be like, you can think like additional text encoder we are adding it, so that like after fusing the input features, we are again adding a one more text encoder before feeding it to the LLM space. That's why it is called some kind of mapping. For example, we have the audio and concurrent text token, and then LLM tokens will be there. So there will be a dimension mismatch can also be there, but this dimension mismatch we can take care using the text encoder. So text encoder, it can project from one, for example, 1024 dimension to maybe 2048 dimension. We can scale it up actually with this text encoder. That people commonly call it as a token mapping. And next slide. Okay. Next one is actually like So this is almost similar to the previous one, but then there will be additional we can have additional embedding space actually, where additional text token mapping text encoder we use separately, and from that we combine this concatenate together. So along with audio we can separately compute the features of text and then combine together. This is like a second time actually we are doing this text coding combining before feeding it to the LLM. So this is like the previous case token we are projecting it, whereas here actually after getting the concatenated tokens, again we have taken the initial text encoder output, and then again we are combining and making this like it's like a concatenation we are doing it and feeding it to LLM. So this is the third type people use it in how to fuse the features, right? That's this is how people do it. Next slide. Okay, so as I said earlier, like we usually do, represent the speech, right? Either in a discrete representation or continuous representation. So mostly people use some kind of unsupervised learning methods. People use it. For example, Whisper or the features from the Hubert or anything we can use it. And from that features, we can either directly use all the features or like maybe convert into instead of keeping it in 2024, maybe we can discretize it to some few tokens. That's why it's like basically limiting the number of token space. That is what people do it in discrete tokens. And this will be useful if you want to do some kind of compression in the our input feature before feeding it to our LLMs. In those cases, actually, discrete sequence coding is helpful. Like any place we are doing to do some kind of encoding and decoding kind of task, there it is more useful. That's why like valley kind of architecture where people try to go from this it's like a encoding decoder kind of architecture where convert the audio space into some kind of discrete reduce the number of space, and then from that again actually go back to the waveform. So in some in those kind of speech generation task, discrete sequence modeling is more helpful. Whereas like in some of the tasks like translation and as well as in speech recognition tasks, this continuous sequence modeling is more helpful, where actually you don't compress that number of units, actually keep it as it is and then use it for the next LLM task. And some of the examples I put it here. But basically you can think like the future representation, whatever we are getting from the speech LLM, we can put it in two kinds. One is discrete representation and second one is a continuous representation. Next slide. Hello. Okay. Yeah, with this background, this you can think like some kind of literature, what's happening in speech LLM. Then we started exploring actually speech LLMs. We tried multiple methods like with speech GPT. We tried to see actually can we implement audio LLM, Palm, something like that. But then when we done some initial experiment compared to speech GPT, this Salman architecture found to be more useful. For at least for our task. So we started with Salman. Salman is actually from the Byte Dance people. They initially proposed it, and then basically it is a speech, audio, language, music open neural network. Basically, they tried for both music as well as the speech task. So they combined both music as well as speech as a modality for the LLM. And some of the key components in here is actually like they use two encoders. One encoder is for the speech, and second encoder is for the music or like non-audio events. And then to project the from audio space to text space, right, they use some kind of queue former that I explained earlier. So they also instead of simply using queue format, they also tried the windowing actually. So because speech actually is a varying audio, right? The audio length can be keep varying. So what they done is they try to any audio, they try to put it some fixed window, and then whenever there's a audio length is more than this window, then they'll stack together actually. So if it is a for example, if you imagine like 5-second audio, but if window length is 5 seconds, but if the total audio is 30 seconds, then 5-second audio keep stacking together feature and then feeding to LLM. So that's why they call it as a window level queue former. And then other thing is they are LLM they use is Vicona LLM, which is basically again a Llama model, Llama LLM they use. It's around I think 8 billion parameter, but then it is fine tuned for the some kind of multi-task they tried, like a translation, recognition, and some kind of task they tried. That Vicona LLM they took it, and then in the Salman paper they also try to add the some kind of parameters like weight parameters in the LLM. So that call it as a low rank adapters. Commonly, like basically you can think like LoRa is actually like adding some few parameters so that we can LLM also you can adapt it. Because if you use it as it is, it may be work for only text kind of features, but it may not work for the additional speech feature we are feeding it. That's why they adapted LLM also with this additional parameters. Why people use additional parameter means so that for normal text features, it should work with normal LLM. With this additional weights, LoRa weights, it should work for the Llama kind of, speech feature. So that's why they will do this additional weights update and then train the model. So what we done is we started initially using this architecture and then done some changes that I will explain in the next few slides. Sir, can you go to next slide?
Yes.
Okay. Yeah, so some more details about this architecture. Like in I said two encoders are there. One is for the speech recognition, or like for speech kind of to extract the speech features, they use the whisper encoder, and there is a beats encoder is also there. So that is for the non-speech units. So for example, you can think like audio, right? It will be like both speech and then there will be some non-speech region will be there. So you can think like beat encoder will model these non-speech events, whereas this whisper encoder will be more useful for the speech-related task. We tried to remove the beats encoder and then train the model, but we found out that by keeping this beat encoder, it is slightly giving a better result. So that's why we didn't change this. We didn't try to remove this beat encoder. And then this queue former is basically to convert the audio features into the text base. That's why we kept that queue former. And then LLM and LoRa adapters, I already explained actually. So in the Salman original paper, they try to use the Vicuna LLM, and then they try to add some few weights using LoRa, and then for adapting for the multiple tasks. For example, they try to explore spoken query questions kind of task, or like music understanding task. They used it, and they also try to do the speech recognition, speech translation. So they try to do multiple tasks in a single model. So how they done is initially they train the entire initially what they done is they try to use this LoRa adapter and then this queue former only. Remaining parameter will be remain as it is. Only the queue former waits, and then LoRa adapters they will adapt it for a specific task. So they tried for multiple tasks like speech recognition, translation, and then spoken query, or like LID, something like multiple tasks they tried. In more details you can see in this paper. But then if they train all the tasks together, then it was not working well. What they done is initially they trained only with ASR data like speech recognition. Basically, these queue former weights and LoRa weights, you should learn initially the speech features, and then after that, if you do this in the stage 2 training, if you do the this multitask training, then it was more helpful. That was the learning from the Salman paper. And yeah, so we also like got similar results. So with this, we started with this as an initial for initial exploration, and then try to do one by one we done the changes. So for example, this is a more detailed view of whatever I was explaining earlier. One is like whenever the audio comes, there is a whisper encoder is there. So that will basically extract the speech features. And then there is a beats encoder is there that will extract the non-speech features. And you can see that like it is not trainable. I mean, it's actually freeze. I mean, we are not changing any parameter of that. It is this basically you can think like to extract the features. So we are using these encoders. For example, you can imagine that like earlier we are using some kind of speech basic features to compute the MFCC, right? Similarly, we are using this whisper encoder and beats encoder to extract some of the features, speech related features. And then these features are converted into some text space using this queue former. This queue former act like a some kind of ask its questions, and then some response we are getting for the what are the output we are getting from whisper and beats encoder, right? That response will when we queue formal will ask questions in terms of weights, and then for that we will get some response based on the speech features, and the output of that we are feeding to the LLM. Similarly, we can also have additional prompt questions, a text instruction prompt, which is basically like we are asking what the task we need to do, because here actually we are learning multiple tasks. One is translation task, second is recognition task, third is spoken query, and then music understanding. So multiple tasks you can do that. So what task to do actually, that is we can given using this text instruction prompt. So it's basically some text input. So that again we convert it into some kind of some text embeddings, and followed by it is we combine together and then put it to language model. And here actually whatever whatever is shown in the fire, right? I mean that fire mark, the LoRa and then window queue form, only those words will be updated. Remaining all we kept it as it is. So that's what even Salman architecture also people try it out. And this method like what are the comparable method, right? Like it was performing better than like Llama or for this specific speech task, right? It was performing well actually in this paper. Next slide. Okay, so I mean, I will just give more. Whatever I explained earlier, so I will just give you the more descriptive thing. Like basically, we are passing the audio through the whisper and beat encoder, and which will give some kind of frame level features. And then Q former, what it does is, what are the features? It will divide into some kind of fixed frames. In this case, actually, they use some kind of 17 frames per window. So within each window, 17 frames will be there. And if it's more than 17 frames, it will go to the next. We'll stack together and then keep concatenated together before feeding to Q former. And Q former, it does like it will ask the query for each window of speech features, and what are the response of that will feed into the LLM. And then in LLM, as I said earlier, we are using that Vicuna LLM. And then output of the LLM will be like next token it's predicting. I mean, for this token, so whatever we are seeding it, it will try to predict the next token. That is the job of the LLM. So basically, like if the question is transcription, if you are asking transcribe this sentence, then it will try to predict the next token, which is actually basically a transcription of that. For example, if you try to predict, say that translate it, then it will try to predict the translation. But our data should be like that. For example, audio input will be in English, then translation text will be in, for example, Hindi, then only this will work actually. Otherwise, it will not work. So data also should be in that pairs. Then only we can do this multiple task. Okay, next slide. Yeah. Further, just for example, like for example, if you take some kind of 5.3 second audio, and which is basically the transcript is for that is what is the weather like in India in the month of December. Then, for example, it will convert to number of frames. So it will be basically if it is give some kind of 265 frames. And then Q former will divide into this number of windows, like 16 windows, and convert each into some kind of tokens. And this and in the text prompt we ask actually like give me the transcription of that. This is the prompt actually we are giving, that text instruction we are giving, and then we'll pass it to the Vicuna LLM. And LLM, it will say that, what is the weather like in India? Because our task is just a transcription. We are not asked for the translation. So it will, what is the weather like in India in the month of December? So that will be outputted actually. So here the input will be audio, and then give me the transcription is the input, and the output will be that transcript. What is the weather like in the India in the month of December? So this is what output. This kind of pairs of data we need it. And if you have that data, then we can do this transcription task. for example, if it's a translation task, then for the target language, right, that should be in, if we are planning for a Hindi translation, then it should be in Hindi. Similarly, for any other languages. So if you have that kind of paired data, then we can train such models. Okay, next slide. Okay, any question till now? Till now, I mean, like I was just explaining about the architecture details. Now I will explain about more about the experiment part. But before that, if anyone has question, then I can answer it. Okay, so, if no question, then what we done is like initially, like instead of using all that data together, like we thought like we'll use only open source data and then see actually where we stand, and then we'll do slowly add I mean some additional data, whatever we in-house collected. So what we did is we started collecting the all the data, and we found out that like for ASR we have multiple data set which is having a speech input, and then output will be in transcription that is there. But when we found out that for translation we don't have much database. At least when we initially explored, there was no database. But recently from AI Bharat we have one database called Bhashanuvad. That is only I think last 2-3 months back only it's released. But when we started like some 6 months back, there was no speech database for Indian languages. So that's why what we done is we taken all the ASR data whatever we have, because here at least we have the audio data as well as transcription. We can convert this I mean transcription, source transcription, to some kind of translation using some synthetically we can generate it. So we try to see actually what are the Indian data sets are there. So these are some of the data sets which is there for like 8 Indian languages plus the Indian English. So this is actually like from various like Spring Labs, Common Accent, CMU, multiple places actually they collected data specifically for Indian context and Indian languages. So these are the most commonly used. I mean, most of the data we collected here, and some of the reference we can get it from this paper also, like which is recently accepted in ICAST. So and not all the database for it is there for all the languages, but some of the data is, for example, Spring Lab it has for English, Hindi, and Marathi. Marathi it is not there, so only English and Hindi. So like that. So whatever the amount of data is there, we kept it here. So in the open source, at least we didn't add the NPTEL here at least by removing, because NPTEL a lot of some errors also was there actually. So that's why we didn't add it. But apart from that, if you collect all the data, we got almost 10.8K hours of thousands of hours of data. So what we done is we collected all this data and then we converted into translation using Indic Trans to translation tool. So that details I mentioned in next slide. Sir, can you go for next slide? Okay, but before going that, like we thought like we will do, I mean, for the 3 type of tasks like speech recognition, translation, and spoken query answering, we are able to do all the 3 tasks. But then spoken query answering, it actually depends upon the use case. For example, if you are planning for the healthcare domain, then we can develop a data set for that. If it is for the like call center kind of domain, we can develop it. But then it is a use case dependent. So that's why for this talk we'll not discuss about that, but mostly we'll focus on translation and recognition part. So I will discuss on the translation recognition in the next slides. So as I said, like what we done is we for the training data, like ASR anyway, that open source data we used as it is. We didn't do anything. But for the AST, we don't, since we didn't have the data, so we used the 10.8K hours of data, and then synthetically generated using Indic Trans 2. Indic Trans 2 is from AI Bharat. So we taken that tool and then converted into speech audio. Speech audio is there, and then transcription is there. The transcription is act like a source for us, and then we convert it into other pair. For example, we tried 2 pairs. One is one to many. One to many means for the whatever the ASR data where English transcription is there, we convert it into Indic languages. 8 target languages we tried, like 4 South Indian and 4 North Indian languages we tried. Similarly, many to one. So we taken all the ASR Indic languages and then converted into English. So that is many to one. So again, we got 8 languages, 8 pairs actually. So this is our data for the AST. So you can think like 10.8K hours of data into 8 cross 8. We got the amount of data actually here. Next slide. And for the evaluation purpose, also like we use actually two data set. One is Cuthbert, that is for Cuthbert data set actually having, we want to test also like which is not seen in the same whatever there in the training. So we just complete took the different test set that is from the Cuthbert, that is also from AI Bharat. So where actually it is specifically for the Indian languages. So what we done is those specific Indian languages, we take the 8 languages that is mentioned in the table 2, and we convert it into English actually. So again, we got the amount of hours of data is mentioned in this table 2. And for English, from English to Indic pairs, we use this Swara as a data set. So we converted again English to the corresponding 8 language pairs. And this is one method actually, like to get the data for the speech LLM. But then there are some cases where actually there will be no audio itself actually. So we'll have only the text-to-text translation data. But can we get a audio? So what we done is we use the TTS audio actually for that. So what we done is we taken the source text of this AI text-to-text translation pair and then generated the audio using the TTS. So details of that is mentioned it in table 3. So I mean, you can think like whenever for speech LLM we need the speech and text pairs, but it's very difficult to get this kind of pairs. So if you want, then we need to use at least we need to use some kind of synthetically generated. So we can either use a TTS, or like if you want for translation tasks, we can use some kind of tools like IndexTrans2, or which are the better methods are available. We can use that. This is how we can get the data set. Okay, next slide. Okay. So here actually I will explain about the our experimental setup. Actually, we trained basically for the two tasks. One is for AST task, that is speech recognition, and second is speech translation task for the Indian language. So here basically we are focusing for Indian language along with the Indian English. We tried with two training paradigm. One is actually like first paradigm we call it a TP1, where actually we trained only with ASR data and then see its performance. And the second one is actually pre-trained the speech LLM with the AST data only. I mean, just to verify actually, do we need a two-stage or not? For example, in the TP3, where initially we tried with ASR data and then second we trained with the AST data. So that is called TP3. I mean, just to see actually whether whatever the paper mentioned in the Salmon paper, that is validate, or like do we need to just directly go with TP2? That is for if you are planning for AST task, right? Can we directly go with TP2? That's why our purpose actually we tried this approach. And then in terms of model, actually we tried with default whatever it is there in the Salmon architecture, that is the Vicuna 13 billion model. And then we try to change the that to recent Llama 3.18 billion model. And also we tried with Krutrim LLM, so that I will explain later. And then for the speech encoder, right? For speech encoder also we need to use some of the any speech encoder. We tried with multiple encoder. We found out that Whisper large is gives good results compared to all the for all the speech encoder, because like one of the advantage of Whisper is already trained for this specific task like ASR, AST, or like spoken language thing. So it is a task specific learned. Whereas if you take any Hubert or Wave to Wake, it is it's just unsupervised way of training. It is not learned for specific task actually. It is just gives speech representation, but this representation not learned for any specific task. That's why maybe like Whisper we got slightly better results. That's why I mean even though we got a results, but then the results with other models were bad actually. That's why we just kept Whisper as in this paper. Next slide. Yeah, so this is the results we got it for the ASR. So here actually basically we just trained for the ASR task. The baseline means actually the by default whisper model. What are the results we got? Get it as usually like generic ASR means we taken some held out test set actually whatever there in our training, right? We divided into 90 and 10 90%, I mean 80% and 10 division we done for development and test set. That with that test set actually we tried to decode with the whisper, and you can see that like if you just if you don't train the whisper model with our indic context, right, then the word rate is very high actually. So if for example English Hindi at least whisper is trained, that's why we can see that the numbers, for example English is around 23% Indian English, but if you go to Hindi slightly it's more, but all other languages is very high actually, because whisper model is by default not trained for Indian context or Indian languages. So we need to fine tune it actually. So then only we will get good results. Similarly, if you say for the Swara and Katbat data set, right? Swara is only English, whereas Katbat for other Indian languages, we got similar numbers, slightly higher numbers. After that, what we tried is now actually the speech encoder is there. Then we can fine tune with the speech LLM. So in the M1 model, right, that is actually basically Vicuna model. After fine tuning with ASR data, then we got the results whatever shown in this generic ASR table. And similarly, we also compared with the Llama model. So compared to Vicona, if you use the Llama model, it is giving a better results. Like if you see across the data set, both generic ASR, Swara and Katbat, you can see that numbers are better for almost all the languages except almost all languages it was giving good results. And basically like another thing is Vicona model is 13 billion, so it's a slightly bigger model, whereas the Llama is actually 8 billion model, but still you can see that like 8 billion model is outperforming the Vicona model. Maybe like it's a recent architecture and then maybe trained with the better model, I mean better data, but what I want to convey is just in number of parameters doesn't matter, how well we train that, right? That is also very important. So you can think like from compared to 13 billion Vicona model, Llama model was giving better results with the M2 training, whatever we got it, the results. This is the results for the ASR. Then we also trained the AST task. So it's there in the next slide. Yeah. Another important thing I missed out is what are the metric we use is word rate, whereas in the for AST task we use the blue score actually. So where actually like higher the number it's better. So here actually this task is basically in the whatever the number reported is from Indic language to English. So that is the number. And then finally, it's for multiple languages. If you see the first row, it is like from Hindi till Kannada. So it is Hindi, Marathi, Gujarati, BN means Bengali, Tamil and Telugu, T means Telugu, and then ML means Malayalam, and then KN means Kannada. So from this language to English we are going. And then I also reported the average number. And here we compared with multiple models. One is by default the Whisper 1 billion model, which because Whisper also support this translation. By default Whisper support this translation thing. And we also fine-tuned for the AST task because we thought like by training with our data, right, it may give better results, but still when you compare actually still Whisper is not performing very well actually. So we also compared Whisper with the Vicona model which is 13 billion, and then Llama 3.18 billion model. And like similar to previous Llama model gives slightly better results across the languages, and in an average term if you see it gives slightly better number. And then the last row, that is Llama TP3, right, it is there in last row. So what we tried is initially we trained the ASR and then followed by the AST training. So it's a two-stage training, whereas in the first case in the TP2 we are just training directly with the AST data. So if you do the two-stage training, slightly we can get a better numbers, like some around 1% improvement was there. So that's a general observation. Like if you do the two-stage training, we can get the slightly better results. And similar to the earlier ASR observation, here also like compared to Vicona 13 billion model, when we trained with Llama 8 Llama 3.1 8 billion model, we got a better number. So better LLM also gives a better results. So that is also another interesting observation here. Next slide. Yeah, here actually like we went other direction. For example, moving away from the um, like EN to Indic language. So in the previous slide, I was showing the results about Indic to EN. Here actually the reverse way we are training actually, like Indic to I mean English to Indic. So here also again the similar observation. Like we got better results with the Llama 3.18 billion model. Here we didn't show the Whisper because Whisper only perform from the other language to English. We tried to do the other direction, but then numbers were very bad. That's why we didn't report it in this paper. And also in this slide, we didn't report it. So in general, like this is a single model. Like what I want to convey is like a single model. You would support both like ASR as well as it will support the AST, and it also support the in both the direction actually. So we didn't train as two separate model. It's a single model support EN to Indic and Indic to EN also. And you can think like in earlier case actually we are training only single language. We are doing it like for example. If you take Indic trans 2 or any other models, it is a language specific model we need to train. But here actually like multiple languages we can train together, get both transcription results, ESR results as well as the translation results. So that's the advantage of speech LLM. Still exploration is going on, but this is like I mean this looks very promising, and this work is also accepted in our this ICAST. Next slide. Okay, just further improvement, like what we done is on the top of the what are the data set we would open source it, we also use some in-house data, and then here actually I just reported the just the average number instead of showing too many tables, too many rows and columns in the table. So you can like see that like initially we started with Vicona compared to Vicona Llama model gives better results. Then we additionally increase the I mean, we use the in-house data, and then the average number increased EN to Indic around 35 blue score, and Indic to EN also improved. Then further, initially we are training only one epoch. Then further improvement you can see if you do the additional training. But then in the here actually in the fourth row, when we use the Krutrim LLM model, which is actually a Llama model only, but then on the top of that we fine tune for the Indic data actually. I mean, Indic data means text-to-text data. We trained it for the Indic sense. I mean, LLM itself is separately trained for the Indic context. So if you use that, then further you can see that there is an improvement you can see in both the direction. And then further we added the recent Bhasha Anuvad. That's what I was saying. The Bhasha Anuvad and NPTEL data, then we can get around 46 and 30 as a blue score. I mean, this is actually like the recent results we got it. That's why this we didn't put it in a paper because we got this results later. So this is actually like with the better model and then better data, right? Amount of data actually we can get a better result. So that's and also it is a single model which will do both direction. I mean translation in EN to Indic and Indic to EN. And I think some demo is also. I mean, if you want someone wants to try, then you can go here and then try that in this particular website. Next slide. Okay. I just want to. Okay. But we need some login. I thought I will show it with.
Yeah. So
if
actually,
possible,
this is required.
with the. I mean, if I am able to share, then I can show it. Maybe if recording is off, then I can show it, I guess. Maybe later in the end of the, maybe if required, I'll show it actually once.
Yes.
Okay. I will just conclude it. Then maybe after that we can, if possible, I will show the demo also. Maybe in the last slide we can go actually. I will conclude the session. Yeah. Yeah, so basically like till now actually we discussed about like how to integrate this voice interface to the LLM. and see actually for the what are the for the different application. Like currently I was showing for translation and speech recognition, but you can also extend for the multiple tasks like spoken query, language recognition, or language understanding, speech summary, something like that. And also like basically we can do with single model we can learn the multiple tasks. So that's the conclusion. And so far actually people are able to do this. At least we tried for the Indian context, but Indian languages we are able to do that. And then future direction is like we are getting very good results, but the only thing is like latency is slightly higher. Like we are getting around 500 to 600 millisecond, but that is not useful for the production use case. It should be less than 100 milliseconds. So that is difficult to get it, because the model size actually we are increasing. Like we are going for like 8 billion LLM, right? So 8 or 13 billion some model size. So the latency also will be higher actually. And also currently we explore for the recognition translation task, how to expand, I mean for the multiple task, right, that we need to explore it. If someone is interested in this kind of research, right, they can explore the multiple task in this direction. And also another important thing is getting the training data. Like whatever we tried is with the synthetically generated, and who are doing it also, like many people are using only synthetic data. If you have the real life data, then I think we can get better results with speech LLM. And also another thing is like if you know actually like in the normal LLM people use RAG is actually like when you, for example, if you ask any question to chat GPT, right, if you want some um, for example, if you ask the flight status, it will respond it, but it also not the real time information. Real time information it should get from the RAG. This they use some, one method called retrieval augmented generation. With that we can get the live status. But for the speech LLM, since it's in speech embedding, there is no text actually input intermediate. There is no text input, so it's very difficult to retrieve that information. How to integrate that is a very challenging. So if someone is interested in speech LLM kind of task, I mean, which is very innovative and then new task, people are doing it. So these are some of the common direction I think people look into it. Yeah, with this I'm concluding. And in the next slide, some references are there. If someone interested, they can go through it. Yeah, that's it from my side. If any questions, I can take it.
So if you have any questions, then please ask.
Just out
No
of
question?
curiosity, yeah,
Yeah,
just
sir.
one small. Out of curiosity, you said that the time is 700, 600 millisecond or so, but has any app been developed which in Indian languages, which sort of is in the public domain using these LLMs?
Yeah, sorry. Actually, it is there. Actually, I want to show the demo, but I think when recording is on, I cannot share it. So that's the problem. Otherwise, I can show it actually. I mean, it is 500 milliseconds. Still, we cannot see the difference. But actually, if some production use case, people may feel the delay. But actually, we put it in a cloud. Actually, it's there actually. So some latency is there, not too much, but still, for the actual use case, maybe that delay is too much. But for our use case, right? I mean, just for understanding point of view, it is that I can show the demo actually, sir. But during the recording, it was not allowing to me. Once I think if recording is off, then maybe I can show it.
That's okay. Yeah, it's just that it is there. Such an app is there. Is
Yeah, it's
just
there,
what you
sir. Actually,
made.
cloud
Thank
app
you.
is there. Yeah.
Hello, Nagaraj, I have stopped the recording. If you wanted to share, show something, then.
Sure. Okay. Okay. Still, it's not allowing us.
Okay, no issue.
But if someone is interested, they can log in and then the Krutrim Cloud app, then they can try it out actually.
Okay, okay. So they have to
And that
sign up
link I
and
shared it in the slide actually. So people who are interested, they can click that, and they need to create account and then see that demo actually.
okay, 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 okay. So I think there is no other questions. For giving such a nice presentation.